If you've ever wondered how an autonomous car can see the world around it, how archaeologists discover entire cities hidden beneath dense forests without excavating a single inch, or how scientists can precisely measure the speed of glacier retreat, you're about to discover the answer. A few years ago, when we talked about topographic mapping or advanced detection systems, we needed enormous, expensive, and extremely complex equipment. But today, there is a technology that has revolutionized this scenario and is present in many more places than we imagine. This technology is LIDAR. In this video, we will dive into the details of how this system works, understand its most surprising applications, and discover why it has become so important in various areas of modern engineering. LIDAR is the acronym for Light Detection and Ranging. At its core, it is a remote sensing technology that uses laser pulses to measure distances with extreme precision. The basic principle is simple and brilliant at the same time. The LIDAR device emits laser light pulses toward objects and surfaces. When this light hits something, part of it is reflected back to the sensor. The time the light pulse takes to go and come back is measured with extreme precision. Imagine a bat using echolocation, but instead of sounds, we use light, and an extremely precise and fast light. Since we know that light travels at a constant speed, approximately 186,000 miles per second, calculating the distance becomes a matter of simple math. We multiply the speed of light by the time the pulse took to return and divide by 2, since we only want the distance to the object, not the complete round trip. What makes LIDAR so powerful is that it doesn't emit just one light pulse, but thousands or even millions of them per second, creating an extremely detailed three-dimensional point cloud of the environment. Each point represents a location where the laser hit a surface and returned to the sensor. To make all this possible, modern LIDAR systems combine several crucial components. Number 1, the laser emitter, which produces light pulses at specific wavelengths, usually in the near-infrared spectrum, invisible to the human eye. Number 2, the optical receiver, responsible for capturing the reflected light. Number 3, the scanning system, which directs the laser at different angles, allowing an entire area to be mapped. Number 4, GPS and inertial systems, which accurately record the position and orientation of the sensor during data capture. Number 5, advanced computers and software, which process this enormous amount of data and build usable three-dimensional models. A fascinating characteristic of LIDAR is its ability to see through certain materials. For example, laser pulses at the right wavelength can partially penetrate water, allowing bathymetric HD-depth mapping in coastal areas. Similarly, some specialized LIDAR systems can partially penetrate vegetation, revealing the contour of the ground under dense forests. It's as if LIDAR had a type of X-ray vision, but limited and based on real physical principles. But how did we get to the sophisticated systems we have today? LIDAR's journey is fascinating and reflects the accelerated advancement of technology in recent decades. The first experiments with the technology that would become known as LIDAR began shortly after the invention of the laser in 1960. In the early 1970s, NASA began using rudimentary LIDAR systems to map the surface of the moon. But these early systems were enormous, extremely expensive, and limited in their capabilities. A single airborne LIDAR system could occupy a large part of an airplane and cost millions of dollars. The real revolution began with the miniaturization of components and the advancement of computational capacity. What once required refrigerator-sized equipment can now fit in the palm of your hand. This miniaturization, combined with the dramatic reduction in costs, has democratized access to LIDAR technology. Today, we find LIDAR sensors in common devices such as robotic vacuum cleaners, and of course, as an essential component in autonomous vehicles. The evolution doesn't stop there. Modern LIDAR systems are capable of capturing not only distance, but also other properties such as return intensity, which can indicate different materials, and even multispectral data, further expanding their applications. Now that we understand what LIDAR is and how it evolved, let's dive into the real world to discover where this technology is being applied. What makes LIDAR so revolutionary is precisely its versatility. It can adapt to completely different needs in fields that seemingly have nothing in common. Let's explore the main sectors where this technology is making an impact. Perhaps the most well-known application of LIDAR currently is in autonomous and semi-autonomous car systems. In these vehicles, LIDAR creates a three-dimensional map of the environment in real time. allowing the onboard computer to identify other vehicles, pedestrians, cyclists, obstacles, and even lane markings. The main advantage of LIDAR for autonomous vehicles is its extreme precision in measuring distances, significantly outperforming traditional radars and cameras in many aspects. A good LIDAR system can detect objects more than 650 feet away, with an accuracy of just a few inches. However, there is an interesting debate in the sector. While most companies consider LIDAR essential for full autonomy, Tesla, under Elon Musk's leadership, has opted for an approach primarily based on cameras and radar, arguing that LIDAR is unnecessarily expensive. This is a debate that continues to evolve as technology advances. Moving from modern roads into forests that guard the secrets of ancient civilizations, we find one of LIDAR's most surprising applications. Airborne LIDAR systems have revolutionized the discovery and documentation of archaeological sites, especially in areas of dense vegetation. The most emblematic case occurred in Guatemala, where researchers using LIDAR discovered more than 60,000 previously unknown Mayan structures hidden under the tropical forest. This discovery revealed that the Mayan civilization was much larger and more complex than previously thought. LIDAR accomplishes this because, by sending millions of laser pulses, some of them manage to pass through the small spaces between leaves and branches, reaching the ground. Modern software can then filter out returns from vegetation and create a digital model of the bare terrain, revealing small variations in topography that may indicate structures built by humans. This capability has been applied to cultural heritage around the world, from hidden temples in Southeast Asia to ancient Roman roads in Europe, now covered by forests. It's as if LIDAR gives us a type of time machine that instantly reveals what would take decades to discover through traditional methods. From remote polar regions to the urban environments where most of us live, LIDAR is also revolutionizing how we build and manage our cities. In the urban context, LIDAR is transforming how cities are mapped, planned, and managed. Urban LIDAR surveys can, number 1, create detailed 3D models of entire cities, including buildings, infrastructure, and vegetation. Number 2, allow precise simulations of noise propagation, air pollution, and natural lighting. Number 3, plan telecommunications infrastructure, such as 5G networks, identifying optimal locations for antennas. Number 4, assist in planning evacuation routes in case of emergencies. Cities like Singapore and Amsterdam have invested in complete digital twins of their urban spaces based on LIDAR data to improve urban planning and management. These virtual models allow interventions to be simulated before implementing them in the real world, saving resources and avoiding costly mistakes. Moving away from the concrete of cities and back to nature, we find LIDAR applications that are transforming how we manage our natural resources. The forestry sector was one of the first to widely adopt LIDAR due to its unique ability to map both the canopy and the ground below the trees. This allows, number 1, more accurate forest inventories, including volume and biomass estimates. Number 2, optimized planning of harvesting operations and road construction. Number 3, monitoring forest health and early detection of pests. In agriculture, LIDAR is enabling a new level of precision. Number 1, detailed maps of microtopography to optimize drainage and irrigation. Number 2, analysis of individual plant structure to monitor growth and health. Number 3, guidance for autonomous equipment, such as tractors and sprayers. This ability to monitor and intervene with millimeter precision is transforming agriculture into an increasingly sustainable and productive activity, optimizing the use of resources such as water and fertilizer. And finally, we come to something you might not expect. LIDAR is already much closer to you than you might imagine. Surprisingly, LIDAR is already present in our daily lives, often without us realizing it. Number 1, in the most recent iPhones, where the LIDAR scanner improves the augmented reality experience and helps with low-light photography. Number 2, in premium robotic vacuum cleaners, which use LIDAR to map environments and navigate efficiently. Number 3, in some commercial drone models, allowing autonomous flight and obstacle avoidance. Number 4, in augmented reality games and applications, improving interaction with the real environment. This increasing presence in everyday devices is a clear indicator of how LIDAR is becoming a ubiquitous technology, following a path similar to what we saw with GPS and digital cameras. Even with all these impressive applications, it would be unfair to present LIDAR as a perfect technology. Like all innovations, it faces its own obstacles. Despite all its remarkable capabilities, LIDAR still needs to overcome some significant challenges. Number 1. Cost. Although prices have dropped dramatically, high-quality LIDAR systems can still cost tens of thousands of dollars. Number 2. Environmental conditions. Rain, snow, fog, and dust can interfere with laser pulses, reducing the system's effectiveness. Number 3. Data processing. The enormous amount of data generated by LIDAR systems requires significant computational power and sophisticated algorithms. Number 4. Energy consumption. LIDAR systems can have considerable energy consumption, a challenge for mobile or remote applications. These challenges, however, represent opportunities for innovation and are driving the development of the next generation of LIDAR sensors. So, where are we headed? If the present of LIDAR already seems impressive, the future of this technology promises even more revolutionary advances. Number 1. Solid-state LIDAR. With no moving parts, more compact, robust, and cheap, accelerating adoption in consumer vehicles. Number 2. Flash LIDAR systems. Capable of capturing an entire scene with a single pulse, ideal for high-speed applications. Number 3. Integration with artificial intelligence. Combining LIDAR data with advanced AI algorithms for real-time interpretation. Number 4. Quantum LIDAR. Using quantum physics principles to achieve unprecedented sensitivities. Number 5. Continuous miniaturization. Chip-sized sensors that can be integrated into virtually any device. One of the most promising developments is solid-state LIDAR, which eliminates moving mechanical components through technologies such as MEMS, microelectromechanical systems, or optical steering. This not only reduces size and cost, but also increases reliability, crucial for applications such as autonomous vehicles. Companies like Velodyne, Luminar, and Ouster are at the forefront of these innovations, competing to develop more compact, efficient, and accessible sensors. This fierce competition is accelerating the development of the technology, benefiting all sectors that use LIDAR. LIDAR represents one of those technological advances that are silently transforming various sectors of society, from archaeology to autonomous driving, from environmental monitoring to urban planning. This technology offers a new level of precision in how we map and interact with the physical world. It's fascinating to think that the basic principle, measuring the time light takes to go and come back, is relatively simple, but its applications are extraordinarily diverse and complex. As costs continue to fall and capabilities increase, we can expect to see LIDAR in even more everyday applications. Perhaps in a not-too-distant future, LIDAR sensors will be as common in electronic devices as cameras are today. If this video helped you better understand how LIDAR sensors work and their multiple applications, subscribe now, because here we always go beyond the surface. Also, leave in the comments which LIDAR application you found most interesting or suggestions for future videos about cutting-edge technologies. See you in the next video.